Alright class, you're welcome to another video lesson. Now in today's video lesson, we're going to be talking about chemistry of carbohydrates. Now this video is going to cover the introductory aspect into carbohydrates, the classification of carbohydrates, and then we're also going to be discussing the reactions of carbohydrates. So it's going to be a lengthy video, alright? So I will want you to sit back and enjoy this video lesson. Please get a book and pen and jot things down, because for some of you in the A level, all right, probably in Unibel or Unidel or any other school, okay, you will need this very well. All right, so questions usually come from the area of carbohydrates, even proteins and fatty acids as well. All right, now let's go into carbohydrate. What then is carbohydrate? Now a carbohydrate can be simply defined, all right, as organic biomolecule containing carbon, hydrogen, and oxygen. So a carbohydrate is a biomolecule that is made up of, so basically carbohydrates are compounds, all right? They are compounds that are basically made up of carbon, hydrogen, and oxygen. So all carbohydrates, I would like to explain that all carbohydrates are made up of three elements. What are the three elements? Carbon, hydrogen, and oxygen. All carbohydrates are made up of carbon, hydrogen, and oxygen. All right, now we've established this part. Now, another way we can also define carbohydrates is that they are polyhydroxyaldehydes or ketones. All right, we can also define carbohydrates as well. Polyhydroxyaldehyde or what? Ketone. So it therefore means that you have some carbohydrates that has the aldehyde functional group, and you have some carbohydrates that have the ketone functional group. Please don't forget, when we're talking about the aldehyde functional group, we're referring to what? We're referring to the CHO functional group. And when we're talking about the ketones, we're referring to what? C double bond O functional group. All right. So take note, the formula for carbohydrates is this: CN H2NON, CnH2NON, where N is equal to the number of carbons. All right, N refers to what? The number of carbons. So if we say N should be 6, for example, we say N should be 6, so we'll now have C6, H, 2 times 6, 12, 12, O6. All right, so this will now give us a very famous carbohydrate that we all know, which is known as what? Glucose. All right, so although this is the formula for glucose, right? Now this is also the formula of other carbohydrates, right? Other monosaccharides that have 6 carbon. This is empty. So what differentiates, for example, this is also the formula for galactose. But what differentiates glucose from galactose is the structure, the way they are being drawn, all right? And carbohydrates can be drawn in two structures, especially for the simple carbohydrates. There are two ways of representing it. Now we have what is called the Fischer projections. We have the Fischer projections, and we also have the Howard projections. The Howard projection is when we are trying to represent the carbohydrate in form of shape, something like this. For example, you have something like this. Carbon here, carbon here, carbon here, carbon here, carbon here. So probably there's oxygen here. So 1, 2, 3, 4, 5. Then have another carbon here. So this kind of way, all right, of drawing it is called the Hayward projection. Then we have this Fischer projection. And for the course of this video, we are going to be working with the Fischer projection. It's a much more simpler structure. So when you just see things like this, for example, you have something like this, CHO. Then you just have an arrow, or sometimes you can also do it like this, just an arrow here. So you can now put, or let's just put the CHO. You just put something like an arrow, something like this. So probably have CH to OH, something like this. Then you can be having H, OH, and OH, then H. So these junctions are carbons. So 1, 2, 3, 4. So there are 4 carbons. Alright, so this is what is called the Fischer projection. So like I said, in the course of this video, I'm going to be focusing on the Fischer projection. Alright, now let's go through the classification of carbohydrates. Classification of carbohydrates. So now let's look at the classification of carbohydrates. Now I'm going to simplify this in the most simplest form. All right. So now take note. Carbohydrates can be classified basically into 3. Right? Carbohydrates can be classified basically into what? 3 groups. Okay. So the first we have the monosaccharides. Next we have the disaccharides. And lastly we have the polysaccharides. Now, what are these monosaccharides we're talking about? Monosaccharides are carbohydrates that contains 1 sugar unit, all right? They contain 1 sugar unit, all right? Now, please also don't forget. Now, monosaccharides, they are also called simple sugars. Now, this is not all for monosaccharide. We are going to expand on this. But before we expand on this, let's just run through these others. Then for disaccharides, they contain 2 sugar units. We are also going to expand on these disaccharides a little. Then for polysaccharides, they contain above 10 sugar units. It contains what? Above 10. Although there's an intermediate between the disaccharide and the polysaccharide, all right? And that is the oligosaccharide, all right? Some sources will say that the oligosaccharide, now some sources will say oligosaccharide, it contains 2 to 10 sugar units. Other sources will say oligosaccharides contains 3 to 10 sugar units, all right? So I prefer 3 to 10. Okay, so the oligosaccharide is between the disaccharide and polysaccharide. But what is generally commonly known, all right, is that carbohydrate is classified into 3: monosaccharide, disaccharide, and polysaccharide. Now let us discuss monosaccharide in proper, because in the course of this our video lesson, even on the reactions of carbohydrates, we are focusing on the monosaccharide. All right, so now let us discuss the monosaccharide in proper. Let's talk about the monosaccharides. Now, for the monosaccharides, remember we've established the fact that monosaccharides are called simple sugars and they contain 1 sugar unit. Now, what are examples of monosaccharide sugars? Now, before we go to the examples of monosaccharide sugars, it is also important for us to state the composition of different monosaccharides. Now, I would like to do it this way. Now, a monosaccharide contains between 3 to 6 number of carbons. All right, monosaccharides, they contain between 3 to 6, all right, number of carbons. All right, so it's from 3 to 6. All right, 3 to 6. So now monosaccharide with 3 carbons, they are known as what? Triose, e.g. glyceraldehyde. Monosaccharide with 4 carbons, they are known as a tetrose. All right, so we'll look at the example of that. The one with 5 carbons, they are known as pentose. So we also look at an example there. Then the one with 6 carbons are known as hexose. So now looking at the example, for the hexose, we have glucose and fructose, which are the most common. Glucose and fructose. For the pentose, we have ribose. We also have arabinose. Then for this, we have erythrose. So these are all of them. Now, please, also very important, take note. Monosaccharides with aldehyde functional group. Monosaccharides with aldehyde functional group, they are known as aldose. That is monosaccharides with the aldehyde, that's the CHO group. Then while the ketose, that is monosaccharide with CO, that's the ketone group. Now a good example of the aldose is glucose, and a good example of the ketose is fructose. So fructose has a ketone group, while glucose has what? A CHO group. Now this is the reason why glucose is a reducing sugar. Now glucose is a reducing sugar simply because it has the aldehyde group. So the presence of these, all right, makes glucose a reducing sugar. Now, glucose is not the only reducing sugar. There are also some disaccharides, all right. There are also some disaccharides and even monosaccharides that are also reducing, all right. So, but glucose, as one of the most common examples, all right, glucose is a reducing sugar. It is a strong reducing sugar, all right. So this is it. Now, why is it that glucose is a reducing sugar? Is because it has the CHO group, which is the aldehyde functional group. All right. So let us go into the disaccharides. We've already established a general idea about the disaccharide. We said that the disaccharide contains 2 sugar units. All right. Now, that is not everything about the disaccharide. Now, they contain 2 sugar units. All right. One way you can also see a question is, what is the bond that holds the 2 sugar units in a disaccharide? Now, I want to emphasize on this. Now, a disaccharide is formed. A disaccharide is formed from the condensation of 2 monosaccharides. All right, 2 what? Monosaccharides. full stop. All right. So in addition, the bond formed is called glycosidic bond. All right. So this is what we have. Okay, glycosidic bond. Now, a disaccharide is formed from the condensation. So now the reaction that leads to the formation of a disaccharide is a condensation reaction. And what's a condensation reaction? In chemistry, a condensation reaction can simply be defined as any reaction, all right, any type of reaction that results, any reaction that results in the removal of water molecule, all right, H2O. Any reaction that results from the removal of water molecule H2O, that reaction is a condensation reaction. Now I'll show you what I mean practically. Now take this for example, all right. Please, the general formula of the disaccharide is C12H22O11, right? So take for example, you have glucose C6H12O6 combining with another glucose C6H12O6. Now a water molecule is removed, right? A water molecule is removed and we have C12H22O11. So you discover instead of 12 plus 12, 24, we remove 2, so that is 22. Instead of 6 plus 6, 12, remove 1, so that's why we're having 11 here. So this is a disaccharide, okay? A disaccharide. So this is what we mean by condensation reaction. Any reaction that results in the loss of what? Water. All right. And the bond that is formed, all right? The bond that is formed attaching one monosaccharide unit to another monosaccharide unit in a disaccharide molecule, that bond is called glycosidic bond. Glycosidic bond. All right? That's the name of the bond. Glycosidic bond. Glycosidic bond. All right, so we have different examples of disaccharides. We have sucrose, we have sucrose, we have lactose, and then we also have maltose. All right, so lactose comprises of glucose plus galactose. Maltose comprises of glucose plus glucose, and sucrose comprises of glucose plus fructose. Now, I will also want to establish a very important detail here. A very important detail. Please note that maltose and lactose are reducing sugars. Okay, maltose and lactose, they are reducing sugars. All right, so maltose the way it is reducing. Lactose the way it is reducing. Now the bond, the type of glycosidic bond, all right, the type of glycosidic bond that is found in lactose and maltose, right, we call that a beta 1,4 glycosidic bond. All right, the beta 1,4 glycosidic bond, or you can say 1,4 glycosidic bond, right? Then in the case of sucrose, it is the 1,2 glycosidic bond. All right, so that is it. Then for sucrose, however is not reducing sugar unless it has undergone hydrolysis. So that simply means, I would like to put it this way: sucrose does not have any reducing property before hydrolysis. However, once sucrose is being hydrolyzed, it can have a reducing property. But unhydrolyzed sucrose is not reducing. Unlike the lactose and the maltose, the way they are also what reducing. Alright, but sucrose is not reducing. Now the reason of this is because sucrose does not have a free anomeric carbon, meaning that it does not have I cannot take time to start drawing the structure on this, but what I will tell you is that an anomeric carbon is a carbon that is carrying the functional group. All right, especially now usually it's around carbon 1. Okay, but in the case of fructose, all right, this guy, the for glucose, the anomeric carbon which carries the CHO is at carbon 1, same for galactose. All right, but for fructose, it has a ketone which is C double bond O at carbon 2. All right, so this is 1 2. All right, so this guy has his own at carbon 1, this guy has his own at carbon 2. So both the groups are used to form bond, so hence there is no free carbons that can act as what now reducing. All right, no free carbon carrying a functional group, all right, to cause any reduction. But in lactose and maltose, all right, this one is at carbon 1, this one the functional group at carbon 1 at carbon 1, both of them has this aldehyde. All right, so only one of these guys meet with the carbon 1 here is what forms bond with the carbon 4. That is why we call it 1 4. All right, carbon 1 bonds with carbon 4. However, this guy still has a free carbon 1 that can act as what reducing. Same explanation for maltose. All right, so this is everything for disaccharide. Now let's go to the polysaccharide. All right, so we're looking at polysaccharides. Now what are polysaccharides? Polysaccharides simply, they are polymers of, or you can say they are carbohydrate polymers. They are carbohydrate polymers. Okay, so polysaccharides, they are what? Carbohydrate polymers. So they are polymers of carbohydrate. Now they contain they contain many monosaccharides. They contain many monosaccharide units. Okay, so these polysaccharides, they contain what? Many monosaccharide units. They contain many monosaccharide units, and all of these monosaccharide units are connected to one another by means of glycosidic bond. Are you getting it? All the monosaccharide units, right? All the monosaccharide units in a polysaccharide are connected to one another by means of glycosidic bond. Now we have some complex polysaccharides, all right? We have some complex polysaccharides like chitin and some other examples. But we are just going to be restricting this our study on the foundations, all right? The foundations when you are doing another aspect of biochemistry, all right? But this one we are just focusing doing the organic aspect of it. Then when you move into the biochemistry aspect, you learn other complex polysaccharides or other complex carbohydrates like chitin, all right? So anyways, now let's come back to this. So they are made up of what? Monosaccharide units, all right? And these monosaccharide units are connected to one another by means of glycosidic bond. Now what are examples of polysaccharides? So e.g. we have starch, we have glycogen, we have cellulose, all right, starch, glycogen, cellulose, and okay, these are the common ones: starch, glycogen, and cellulose. Okay, starch, glycogen. Well, I can also include inulin to this. Inulin. So these are the common examples of polysaccharides we have. All right. So all of these guys, they consist of repeating glucose units. Then this one precisely consists of repeating fructose units. All right, consists of repeating fructose units, while this one consists of what? Repeating glucose units. Now we have been talking about glucose, fructose. Now we need to understand the structure, the Fischer projection formula of glucose and fructose, because it's going to help us. All right, so we need to understand the Fischer projection. Now, in order to do the Fischer projection formula of glucose and fructose, remember I already explained how it looks like. Now this for glucose. The Fischer projection of glucose looks like this. Fischer projection of glucose is CHO. This is the carbon 1, which is the aldehyde group. Then we have this OH, H, OH, H, and then if you count now, we have 6 carbons. 1, 2, 3, 4, 5, 6. All right. So this is glucose. In fact, this is what we call D-glucose. This is a D-glucose. How do I know that this is a D-glucose? I know this is a D-glucose because now how to know between for monosaccharides like glucose, fructose, galactose, and all of those other guys. Now, how do you know if it is D or L? Now, please, you are paying attention to the second. You are paying attention to the second to the last carbon. Let me put it that. Or you are simply paying attention to carbon 5. If the monosaccharide is an exose, that means, remember, exose are monosaccharides with 6 carbon. So if the monosaccharide has 6 carbon, to know if it will be D or L, you have to pay attention to the 5th carbon. However, we can generally say that to determine if a monosaccharide is D or L, you are paying attention to the second to the last carbon. All right, this technique works for exose, pentose, triose, tetrose, and all of them. All right. So in the case of an exose having 6 carbon, you are paying attention to the second to the last carbon, which is the 5th carbon. This one here. That's that carbon. So now, if the OH is at the right, it becomes D. If the OH is at the left, it becomes what? L. So if I change this, I put OH here and I put H here. This will now become what? An L glucose. So in order for it to be a D glucose, I will need to put H here and I will turn here towards OH. Alright? So if the OH, if the 5th carbon for an exose, alright, for an exose, if the 5th carbon contains OH at the right hand side, it is D. If the 5th carbon contains OH at the left hand side, it is L. Or generally in all monosaccharides, if the second to the last carbon has OH in the right hand side, it is D. If the second to the last carbon has OH at the left hand side, it is L. So now let us draw the structure of fructose. So fructose becomes CH2OH, C double bond O, then we have CHOH, we also have CHOH, then we have okay, sorry, pardon, we have HOH, then we have this, and lastly we have CH2OH. So how many carbons is there? 1, 2, 3, 4, 5, 6. So you can observe that the group, right, the ketone group is at carbon 2 of fructose. That is why it is 1, all right, carbon 1 of glucose, In the case of sucrose, it is carbon 1 of glucose, all right, forming glycosidic bond with carbon 2 of fructose. That is why it is called 1,2 glycosidic bond. Remember, I stated it before, 1,2 glycosidic bond. That's the reason why. All right. So you can observe that in fructose. Now, is this an N fructose or a D fructose? It's a D fructose because the second to the last carbon, all right, the OH is facing the right. So it is what? D fructose. All right. So please don't forget. In the case of fructose, the functional group, the ketone group is at carbon 2. In the case of glucose, the aldehyde group is at what? Carbon 1. So this guy has aldehyde, so it is called an aldose because it has a aldehyde group. This guy has a ketone group, all right? It is called what? A ketose, all right? So now we want to go into the reactions of carbohydrates. The first reaction of glucose, all right? Now, when we're talking about reaction of carbohydrates, what we usually focus on is on the reaction of glucose. Okay, now looking at the reaction of glucose, the first we have here is oxidation. We know what oxidation is, right? And oxidation cannot occur without the activity of some oxidizing agents. So, and sometimes, all right, the oxidizing agents used depends on what you actually want to get, and the oxidizing agent can affect the type of product from. Take for example, if we use mild oxidizing agents like the Ferlin solution, the Ferlins, or should I just call it the Ferlins reagents? All right, the Ferlins reagents or the Tories reagents, or even um, um, bromine in water. All right, so bromine in water can also act as an oxidizing agent, or you can just use the word bromine water. Okay, bromine water. So now this will cause a mild oxidation to the carbonyl carbon, that is the carbon carrying the functional group, which is this guy. So it's going to oxidize this from an aldehyde to a carboxylic acid. So we're going to have COOH, then COH, we have H, and we have CHOH, we have COH, CH, and then OH. Then we have CH2OH. So this is what we have, all right? So this is what we are going to get for the mild oxidation. Then, however, using strong oxidizing agents, all right? Using strong oxidizing agents like, so this one, when we use Ferlin solution, but using strong oxidizing agent like nitric acid, HNO3, nitric acid, what we are going to get, we are going to get, what will happen is that this carbonyl carbon will be oxidized to carboxylic acid, and this other end will also be oxidized to carboxylic acid. All right, so this is what you get for mild oxidation. Then for a strong oxidation using strong oxidizing agents, all right, this is what we are going to have. COOH, then COH, CC, so HOH, H, then we have OH, then also COH, then we now have COOH, all right. So you have COOH at this point, and you also have COOH at this point. So you have two carboxylic group, all right? So having two carboxylic group. So this guy here, this particular guy is called glucaric acid. Then this other guy is called gluconic acid. All right, so this is what we have. So using mild oxidizing agent like the Ferlin reagent or bromine water, okay, we're going to get gluconic acid. Using strong oxidizing agent like HNO3, we're going to get glucaric acid. Glucaric acid is also referred to as saccharic acid. All right, So now let's go to the second reaction. The reaction of the dehydration reaction. That's the dehydration of glucose. Please don't forget this is glucose. Okay. So let's look at the dehydration of glucose. Now, what is dehydration? Dehydration is a reaction that involves the removal of the elements of water. All right, and it causes a permanent alteration. I will not just use the word permanent, however, but it causes an alteration in the structure of the compound. All right, that's dehydration. So dehydration here is basically talking about removal of elements of water. So we are going to be removing hydrogen and OH. Okay, so now the process of dehydration mostly require the presence of concentrated H2SO4, which is a strong dehydrating agent. All right, conc H2SO4 is, this word conc here means concentrated. So conc H2SO4 is a strong dehydrating agent. So it can cause this compound to be dehydrated, a situation whereby the hydrogens and the OH starts leaving. Now, if you count, you discover that we have in total, just counting all the hydrogens, in total, we have 12 hydrogens and 6 oxygens. So hydrogens 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Oxygen 1, 2, 3, 4, 5, 6. So we have 6. So the OH and the H are going to be removed, all right? So we're going to have this. It's going to be removed in the form of water, H2O. So to balance, we'll put 6. So that 6 times 2 will be 12. We have 12 oxygen. 12 hydrogen, then 6 oxygen. So what is left for us is what? 6 carbon. Alright? So 6 carbon. So this guy is referred to as a black mass of carbon. Black mass of carbon. So this is what we mean by a dehydration reaction of glucose. So please take note, glucose, all right, in the presence of concentrated H2SO4 is dehydrated to what? Just a black mass of carbon. All right, guys, so we have this next reaction, which is a reduction reaction, okay? So this play with the structure of glucose, please don't forget. So we're talking about reduction of glucose. Now, in this reduction, we're going to be emphasizing on something. Reduction has to do with, reducing something, all right? Now, if you take your mind back to organic chemistry, alcohol can be oxidized to aldehyde, and aldehyde can be further oxidized to what? Carboxylic acid or the arachidonic acid. So what this reaction is going to do is that it's going to reduce this aldehyde group, all right? It's going to reduce it to an alcohol, okay? It's going to reduce this aldehyde group to an alcohol. Now, the reducing agent that is used to carry out this reduction, we can have sodium borohydride, aka which is the sodium tetrahydroborate 3. We can also have lithium aluminium hydride, lithium tetrahydroaluminate 3. Right, this one is sodium tetrahydroborate 3. Then we also have amalgam. All right, sodium amalgam and water. We also have sodium amalgam and water. These are also the reducing agents that can be used, all right, to cause reduction. So let us use sodium tetrahydroborate 3. So let's use this as the reducing agent. So what we have to this group is going to be converted to what? An alcohol. So it's now be CH2OH. Then every other thing stays the same. Right? So COH, H, then CH, OH, 1, 2, then this is known as sorbitol. Sorbitol. All right, sorbitol. Okay, so that's the name of this. Or it can also be called, we have glucitol, sorbitol or glucitol. Look at another important reaction of glucose, which talks about addition reaction. Now, this addition reaction is simple. This addition reaction is done, all right, with hydrogen cyanide. So hydrogen cyanide reacts with glucose in an addition reaction process, all right, to give us a glucose, all right, but of a different nature. One thing that is unique about this reaction is that the resulting glucose structure, all right, not just an entirely glucose structure, although the structure has been, some other things have been added, so it's not just called glucose alone, like what you are seeing here. This one is just called glucose, all right. So the important thing about this reaction is that it adds to the number of carbon chains. So if this is 6 carbon chains, 1, 2, 3, 4, 5, 6. So when you react with hydrogen cyanide, it adds an extra carbon to this carbon chain, thereby making it what? 7. If I use another monosaccharide, let's say I use ribose, which is a 5 carbon. So if ribose is to react with this, for example, all right, so there'll be what? An addition of one extra carbon. So what you will not get, instead of being a 5 carbon chain, it will now become what? 6. So one thing that you need to know is that when glucose reacts with hydrogen cyanide, one extra carbon atom is added to the carbon chain, thereby converting it from 6 carbon structure, all right, to what? A 7 carbon structure. Now let's look at it. So the reaction with what now? Hydrogen cyanide. Now what happens is that this is HOH, all right. So one of these H will come here and this OH remains. So you have something like this: COH and then H, all right. So that's for this aspect. Then our cyanide will be above. Then every other thing continues. So this is what we get, all right. So how many carbons atom, all right, do we now have in total? 1, 2, 3, 4, 5, 6, 7. So that's the thing about this reaction, all right. And this is known as glucose cyanohydrin. Glucose cyanohydrin. Now let's look at the next reaction. All right, we are looking at another reaction, the fifth reaction of glucose, which is condensation reaction. This is the fifth reaction. Now remember, I told us earlier on that a condensation reaction has to do with any reaction that leads to the removal of what? Water, right? So this is what we have. So that is why you just see, I just, how to summarize this. So you are seeing minus H2, so it means water has been removed. See the same thing. These two here is just to balance the equation in the reaction. So but what you can see is that here is minus H2O minus H2O. So water is what? Removed. That is what makes a condensation reaction a condensation reaction. Are you with me? All right. So for this first guy, when glucose, this is glucose. Now this structure is similar to the other ones I've been drawing. All right. All these points here, there's a carbon, there's a carbon here, there's a carbon here, there's a carbon here, there's a carbon here. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Then this one 6. So these junctions you are seeing here, there's carbons, all right, in those places. So for this reaction, we are going to get, what we are going to get from this reaction, we are going to get ozyme, all right. And our ozyme is after you remove water, all right. So these are one of these. So we are now left with what? CH double bond NOH. All right. So then we have a normal glucose as C, need it to be short. So we have COH, then H, and then we also have CH, then OH, and then we also have COH, and then H. We also have COH, and then H, and then we have CH2OH. So how many carbons in total? 1, 2, 3, 4, 5, 6. This oxime or glucose oxime, or you can just simply say oxime. Alright, that's an oxime. Then for this second one, we are going to get glucose phenylosazone, or you can just simply say osazone. Now, how do we get osazone? When this reacts with this, alright, we're going to get this CH double bond NNH, alright. We remove water, H2, then H2, and one O left. So NNH, then C6H5. Then for the second one, we have C, then we have C, then same thing, and then we have a bit, so that's 2, 3, 4, then oh, space. So please, you're gonna bear with me. Then please, we also have our C2 H5 at the last here, right? So we still have our CH2OH. That's the last carbon there, all right? So that's the last carbon there because of space. So this is known as osazone. Osazone, all right? Or you can say glucose phenylosazone. Glucose phenylosazone. All right, so that's what we have. So guys, this compound here and this compound, they have a name. All right, so this one here is called hydroxyamine. All right, then this one here is called phenylhydrazine. All right, so when glucose reacts with hydroxyamine, all right, we're going to get oxime, and when glucose reacts with phenylhydrazine, we're going to get osazone or glucose phenylosazone. The reaction of glucose we're going to have is fermentation. Now, what is fermentation? Fermentation is simply the slow microbial decomposition, all right, slow microbial decomposition of, starch, which is a large carbohydrate, to give us a final product, which is carbon dioxide and ethanol. But however, there is a very important intermediate, all right, in the fermentation process that actually produce the carbon dioxide as well as the ethanol, and that important intermediate is known as glucose. All right, so let's take away the starch. We're not going to focus on the starch, so let's just focus on glucose. Now, glucose can undergo fermentation. Now, the fermentation process of glucose, let me just write it chemically, C6H12O6. The fermentation process of glucose is mostly associated with zymase, which is an enzyme produced by yeast. All right, so zymase, we break down glucose, converting it to what? Ethanol, C2H5OH plus water, carbon dioxide, all right, plus carbon dioxide. So these are glucose, these are ethanol, and these are carbon dioxide. So by the time we balance the reaction, we're going to put 2 here, that's 4, put 2 here, that's 6, then 2 times 5, 10, 11, 12, hydrogen is balanced, then oxygen is 6, 2 times 2, 4, plus 2, 5, 6, which is balanced. So this is the fermentation process of glucose. All right, so please, thank you very much for watching to this very and please do it to share this video among your college friends and university friends. Share it to them, let them watch and learn. Exams is fast approaching. So thank you very much, and I'll see you in the next video lesson.